problem with synchronous counters is that many times you need more amount of logic. For example, say this one, here we have got a 3-bit counter, 3-bit synchronous counter, but this 3-bit synchronous counter, so this flip flop 0, flip flop 1 and flip flop 2. So, this flip flop 2 is the most significant bit, flip flop 1 is the next bit and flip flop 0 is the least significant bit. Now, you see that in the connection pattern, so what we need is that at every clock pulse this flip flop 0 should toggle. Okay. So, this is this should toggle, flip flop 1 should toggle if flip flop 0 was equal to 1. Like if you look into this counting sequence, so this whenever this flip flop 0, it toggles at every clock, fine. Flip flop 1 q 1, it changes the state only when q 0 was equal to 1 at the previous time. So, you see whenever this is equal to 1, so it makes a transition. Similarly, this is equal to 1, it makes a transition. But if q 0 equal to 0, in that case it is not making any transition, like here also it is not making any transition. So, it is coming from 1 to 1 only. And as far as q 2 is concerned, so q 2 should make a transition when q 0 and q 1 both are equal to 1. So, here q 0 q 1 both are equal to 1. So, at the next time it makes a transition to 1 and they become 0, that is a different thing. So, while drawing the corresponding logic circuit, so what is required is that for this j and for the flip flop 0, so they will it will transit at every clock pulse. So, this is tied high directly. Now, for this flip flop 1, this j and k are shorted and it is connected to this q 0 line. So, whenever q 0 equal to 1, at the next clock this flip flop 1 will transit. Then this flip flop 2, it is connected again j and k are shorted, but it is connected via an AND gate where this q 0 and q 1 they are ANDed and then this is connected to this flip flop 2. So, this flip flop 2 will transit when q 0 and q 1 both the outputs are equal to 1. Okay. So, this way you can have a 3-bit synchronous counter. Now, if you have more number of stages, like if you are trying to have a 4-bit synchronous counter, then you see that this you will be needing another flip flop here. Okay. So, you will be needing another flip flop here with j and k, the clock signal will be common, clock signal there is no problem. Now, this j and k are to be tied together and then that value should come from another AND gate. Now, this AND gate should have input from this line, okay. It should have input from this line and also so this q3, if we say that this line is say q3, then q3 will transit only when all this q0, q1 and q2 all of them are 1. Okay. So, that is this line should be 1 and this q0 q1. So, this line should also be equal to 1. So, you can make a connection like this and then we will be getting this thing. So, this way I can have another stage of a counter, we can get a 4-bit synchronous counter, but the problem that you can visualize is that you see the further stages that I am connecting. So, the AND gate is I am forming a chain of AND gates. So, the first this flip flop sees the delay of one AND gate, but this flip flop sees the delay of these 2 AND gates to get the correct value. So, if you connect another stage, so it will see delay of 3 AND gates in the process, or you use AND gates of higher number of inputs. So, another possible way of connecting it is that you do this thing and then you take this output, this Q output, this Q output and this Q output and connect it together and then feed it here. So, that may be other possibility, but in that case the AND gate is becoming more complex. So, you are requiring AND gates of higher number of inputs. So, that is the other difficulty. So, this way this synchronous design they have got this type of problem, the circuit becomes complex. Anyway, so many times depending upon the situation we choose between synchronous counter and asynchronous counter. So, here is actually it is shown, that is we have got this 4-bit synchronous counter and this G1 is feeding this flip flop 2 by ANDing Q0 Q1, then this G2 is feeding flip flop 3 via ANDing of this Q0 Q1 with Q2. Okay. And then a 4-bit synchronous binary counter and timing diagram have been shown, So, when the AND gate outputs are equal to high, so they are shown by these shaded portions. So, essentially it will go through this sequence starting with all 0 going up to all 1, and then from the 16th cycle it will be repeating. So, it will be again starting with all 0 and continue like this. So, that is a synchronous binary counter type structure that we have. So, how do we design a synchronous counter? So, the example that I have shown you, so it seems that all on a sudden, so we could land into this particular design, but how do we come to that? So, for that purpose there are several methods that are available for that can follow arbitrary sequence of counters. So, we will first see some JK flip flop based implementation, and since it is synchronous design, so all flip flops are clocked at the same time. So, flip flop clocking is we do not have any opportunity to manipulate the clock signal. So, clock signal is common and it is fed from the same source for all the flip flops. So, all you can do is that you can control these J and K inputs for these flip flops to get your desired sequence. So, the JK excitation table, so it is known to us. Just to recapitulate, so if the present value is 0 and the next value is also 0, so what we have to do is this J should be 0 and K can be do not care. Similarly, from 0 to 1, if the present value of this flip flop Q output is 0 and the next output we expect to be 1. So, for that I need to give J equal to 1 and K can be do not care. Similarly, from 1 to 0, K should be equal to 1 and J is do not care, and for 1 1 I should this J K value must be equal to 0 and this J value can be a do not care. So, this is the JK excitation table. So, that is known to us. Now, so for this is again for JK excitation table from 0 to 0. So, present state is 0 and the next state is 0 and J is 0. So, we already explained. So, 0 to 0 transition, flip flops present status is 0 and it should remain 0 when a clock pulse is applied. That can be either J equal to K equal to 0 or J equal to 0 K equal to 1. So, it is J equal to 0 K equal to 0 or 1. So, that is J equal to 0 and K equal to do not care. So, that explains this table, we have already seen that. Now, for synchronous counter design, so we have to see when these transitions are occurring, like when this 0 to 1 transition is occurring, present state is 0 and it has to change to 1 with J equal to 1 K equal to 0 or J equal to 1 K equal to 1. Similarly, from 1 to 0 transition I can get by K equal to 1 and J equal to 0 or 1, and 1 to 1 transition K must be equal to 0 and J can be either of the value 0 or 1. So, suppose we are asked to design a counter which goes like this. So, this is the sequence that is given to us, that is it says that it is a 3-bit counter. It will start at 0 0 0 and the next time it will go to 0 0 1, then it will go to 0 1 0, then 0 1 1, then 1 0 0, and after that it goes back to again 0 0 0. Suppose this is the sequence that I need to generate. So, in terms of decimal value, so the sequence that I need is 0 1 2 3 4 and then again 0. Okay. So, how do we design such a counter? So, that is what we will try to see. So, the first point, first step for designing such a counter is to draw something called the state transition diagram for the counter. So, it is like this, the initially, so this counter value is 0 0 0, then it goes to 0 0 1 on the next clock pulse, then 0 1 0, 0 1 1, 1 0 0 and going back to 0 0 0. It does not tell anything about what are you going to do for the other states. So, maybe, so if we assume like this, that if you start at any other state, if the by chance the counter reaches any of these states 1 1 0, 1 0, 1 0 1, 1 1 0 or 1 1 1, then at the next clock pulse, so it will come back to this state all 0. So, it will be starting from, so that is the so this is actually the drawing the state transition diagram showing all the possible states, including those that are not part of the desired counting sequence. So, once we are done with this. So, the next step is to use the state transition diagram to set up a table to list all present and next states. So, you see from 0 0 0, if this is the current state, then from this diagram we know the next state should be 0 0 1. So, that is written here from 0 0 0 to 0 0 1, from 0 0 1 to 0 1 0. So, this is coming directly from this table, from this state transition diagram particular. So, when we reach this 1 0 0, then the next state is 0 0 0. So, from 1 0 0 the next state is 0 0 0, and if for other values like 1 0 1 the next state should be 0 0 0, for 1 1 0 next state should be 0 0 0. So, like that. So, this is actually capturing these 3 state transitions. So, 1 0 1, 1 1 0 and 1 1 1 to 0 0 0. Now, so that table is drawn, and since they will be realized by means of JK flip flop. So, each of these bits A, B and C, they will be realized by JK flip flop. So, we try to see what should be the corresponding values of J and K. So, see for this one, so 0 to 0. So, this J bit must be 0, K bit can be do not care from the JK excitation table. So, we know that. Similarly, from say 0, say this is also 0 to 0. So, this J bit is 0 and K bit is do not care. So, at this point at this level, so we have got 0 to 1 transition. For that J bit should be equal to 1 and K bit is do not care. Similarly, if you take any other point, say that this the transitions of the A bit, so 0 to 1. So, for that this J A, that is A input of the J input of the A flip flop, so that should be equal to 1 and K input can be do not care. So, this way we fill up this part. So, this present state, next state, so this is coming from the counting sequence, and once we know that, once we know the counting sequence, so you can derive what should be the control values that should be fed to the J and K inputs of individual flip flops to get the appropriate state transition for the flip flops. After that, the step is you have to make the corresponding combinational logic. So, if the current state is 0 0 0, then we want that J A should be 1 and K A should be do not care. So, that way you write down the truth table. Okay. So, 0 0 0 to 1 1 1, and then what is the corresponding expected value of J A and K A. So, that we can write down, and then you put it into a Carnot map, do minimization, and we see that the function that we are getting for J A is C bar and K A is always equal to 1. Okay. So, J A equal to C bar and K A equal to 1, that is the truth table, that is the logic function for the A bit. Similarly, for the B bit, so J B and K B are to be derived. So, here also we do the same thing, that from that previous table we find out from actually from this big table, you just take out this present state, these 3 bits and these J B K B columns. So, that way we are just rewriting it here, here J B K B column, and then you do a logic minimization by means of Carnot map. So, you see that the function that we are getting is J B equal to A C bar and K B equal to A plus C, and the same thing we do for the C flip flop. Okay. And then we again take out the portions of present state and these J C K C columns, and accordingly draw the truth table and make the Carnot map and do minimization, and J C turns out to be A B and K C turns out to be 1. Once this is done, so we are now ready to draw the circuit. You see that this if we look into any of them, say K C should be equal to 1. So, where is K C? So, this K C is tied high. Similarly, this J C should be equal to A B. So, this J C, this A and B, these 2 bits have been taken and they are ANDed, and this A B is fed to J C. Now, if you go back, see this K B equal to A plus C. Now, you see this K B. So, we are ORing this C output and A output. So, these 2 flip flop outputs are ORed and it is fed to K B. So, this circuit that we are getting, so you see the clock is common to all the 3 flip flops and they are coming from the same source. So, this is a synchronous design, and so if you start it with some initial value, okay, so it will make transitions accordingly. So, it will follow this particular sequence that we have. So, you start it at any of these values. So, it will be producing these values, and if you start at any of these 3 states. So, it will be first transiting to 0 0 0, then it will continually making transitions in this sequence. Okay. So, that way we can design some synchronous counters. We can modify the design a bit. So, we want to design a sequence where the sequence is 0, then 2, then 5 and then 6. Okay. So, the sequence in terms of decimal what I am looking for is 0 followed by 2 followed by 5 followed by 6 and then coming back to 0. Now, how do you say like how many flip flops will be needed? So, that is determined by this number, the maximum count value that you have. So, this since it is 6, for representing 6 in a binary notation we need at least 3 bits. So, that is given by, so if I say that this is the max value that the counter should produce. So, the number of flip flops needed is given by this log of this max, log of this max to the base 2, the ceiling of that. So, in this case this max value is equal to 6. So, this turns out to be equal to 3. So, if you are designing a sequence, so if I tell you that you have to design a sequence like this as 0, 5, 15, 25, 11 and then 0. Then for deriving how many flip flops will be needed, so you have to look into this value 25 and then max equal to 25. So, you will need a 5 bit, you will need 5 flip flops for designing it. Okay. So, that way this log value of this max, so it will tell you how many flip flops will be needed for designing the counter. Now, in this particular case, so we have got we have to design this particular sequence. So, 0 0 0 followed by 0 1 0, 1 0 1 and 1 1 0 and repeat. The undesired states 0 0 1, 0 1 1, 1 0 0 and 1 1 1, they must always go to 0 0 0 on the next clock pulse. So, that is expected. So, it will go to 0 0 0 in the next clock pulse. So, this state transition diagram, so it will be like this, and then you can just draw the present state, next state type of thing. So, it is 0 0 0 to 0 1 0, 0 0 1 to 0 0 0 0. So, that way you fill up this table. So, as per this sequence from 0 0 0 to 0 1 0 like that. So, based on that you fill up this table and then indicate the level required at each j and k inputs. So, that is similar to what we have done previously, this JC and KC for the C flip flop, JB and KB for the B flip flop and this JA and KA for the K flip flop. So, that way we derive the we write down the transition table and then we have to go for the logic circuit. So, for this CBA values to be this and these 3 values. So, what are the values of JC, KC, JB, KB and JAK? So, that part if you write down, then you can make Carnot map and do a minimization for each of these JC, KC, JB, KB and all. And so, for JA turns out to be B C bar, KA turns out to be 1, then this JB turns out to be CA plus CA C bar A bar, KB turns out to be 1, for JC turns out to be A bar B and KC turns out to be B plus A bar. So, now you can the final circuit is not shown here. So, that is just another step. So, you have got 3 counters and then you have got the appropriate logic connected to the J and K inputs of individual flip flops. Next, we look into another example where this is again a JK based synchronous counter that counts in the sequence 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0 and repeat. But all the undesirable states, undesired states, their next state can be do not care. So, we do not bother, like if they start at any of the states which are not stated here, then what the system will behave. So, that is not to be a concern. Okay. So, that is the user will ensure that those undesirable states will never be reached by this counter, it will never start at those states. So, this CBA it can go from 0 0 0, all the 8 combinations can occur, but out of that we are bothered about only these patterns, okay, 0 0 0, 0 1 0, 1 0 1 and 1 1 0. For example, we are not bothered about the state 0 0 1. So, at if the system is at count value is 0 0 1, what will be the next count value, that is we do not bother. So, they are do not cares. Similarly, if the current count value is 0 1 1, then what is the next count value? So, that is not relevant. So, that is do not care. So, this way you can introduce a number of do not cares into your design, and after that you can do a minimization. Okay. So, so if it is 0 0 1 and it is do not care, then all these values are they will turn out to be do not cares. Similarly, we can have this thing, we can have this 1 0 0 and this is do not care. So, they are all going to be do not cares. So, this way we can have this do not cares put into this J, JB, JC, K, KC, KB, KC columns, and accordingly we can do minimization and get the final circuit. So, you can design the logic circuit for this. So, this is we just write down this table again and then do minimization as we have done previously, and then we can make the final circuit. Another example that we take is to design a 3-bit counter with D flip flop with the following sequence. So, this is not based on JK, but it is based on the D flip flop. So, it will count in the sequence 7 6 5 4 1, all unwanted states will go to state 7, and this output sequence is 7 6 5 4 1, then it is like this. So, it is starting at 7, then 6 5 4 1, then again 7, it goes like this. And if it starts at other states, all unwanted states like 0 0 0 0 1 0 and 0 1 1, they go to the state 1 1 1, that is 7. Okay. So, we can so this is the specification of the problem. So, if we want to design it, first of all we need to recapitulate the D flip flop excitation table. So, D flip flop table is very simple. If the present state is 0 and the next state is 0, so D should be 0. So, it is depicted by the next state value that you need. So, accordingly the D value should be set. So, as per our specification from 0 0 0, the next state is 1 1 1. So, this DA, DB, DC, so that is they are going to be 1 1 1. Similar, so 0 1, so for those states, so you see here for 0 0 0 and this 0 0 1, in both the cases the next state is 1 1 1. So, that is done here from 0 0 0 it will go to 1 1 1, from 0 0 1 also it will go to 1 1 1. Accordingly, this DA, DB, DC they should be set to 1. So, it goes like this. So, this way we can think about this, we can make this table, just we were doing it for this JK based counter. So, we can make this D flip flop based counter and get the design. Then we take it to the Carnot map, and in the Carnot map we can have this minimization like this, we can have this minimization for DC, DB and DA. So, they will turn out to be like this: DA is A bar plus C bar, DB is AB plus C bar, and DC is A plus B plus C bar. So, once we do this minimization, so you can draw the corresponding circuit. So, that circuit is not shown here, but essentially what will happen is that you will have this 3 D flip flops. So, these are the 3 D flip flops, and the clock will be common to all of them, the same clock will go to each of them. But this D input, so this is the D input for the A flip flop, and A for the A flip flop it said is A bar plus C bar. So, this is this Q bar line from here, and Q bar line for this is the A, this is B and this is C. So, this Q bar line and A line, so they should be odd and then they should be connected here. They should be odd and connected here. So, in this way you can have the other logic circuit, other portion like say so for say DB it is AB plus C bar. So, this A and B outputs they should be ANDed and ORed with this Q bar output of C, and that should be connected. So, whatever circuit, the way we have drawn the previous circuit, so we can also make this circuit and we can get the realization in terms of D flip flop. So, you can also design counters using T flip flop. So, for example, this T flip flop excitation table is like this: from 0 to 0 transition T should be 0, For 1 to 1 transition also T should be 0. For 0 to 1 or 1 to 0 transition, T input should be equal to 1. So, that is the excitation table of T flip flop. So, now if you go back look into our counter specification, then from 0 0 0 it has to go to 1 1 1. So, this TC, TB and TA all the inputs should be equal to 1. Similarly, from 0 0 1 also we want to go to 1 1 1. Now, in this case you see that A should not transit. So, TA should be equal to 0, TC and TB they should be equal to 1. So, it should go like this, fine. So, once this is done, so rest of the thing is simple. So, from this present state we want to apply TA, TB, TC like this. So, we have to derive the corresponding functions, and then we so this TC turns out to be A bar B bar plus C bar, TB will turn out to be B bar C bar plus A bar B C, and TA will turn out to be A bar plus C. So, that way we can have this Carnot map for this T flip flop, and accordingly we can make the circuit for the T flip flop based realization. So, another important type of counter that we have is the ring counter. So, in ring counter we have got say this initial, it is realized by means of T flip flop, then this initial value of the ring counter is say 1 0 0 0. So, this is T value is, so this T3 value is 1 and these values are 0 0 0. Then since this is a T flip flop and this input is 1, so at the next clock pulse, okay, so this T0 will be making a transition. So, at the falling edge T0 makes a transition and it becomes equal to 1, but rest of the otherwise this is a shift register. So, this that way this is these values are shifted. So, this T2 value, so that was initially 0. So, it comes to this, and then we can have this type of shifting. Okay. So, this is it will be generating the count in the sense that it will first be 0 0 0 1 and then 1 0 0 0, then 0 0 0 1, 0 0 1 0, 0 1 0 0 and 1 0 0 0. So, you can do the same thing by means of this 2 bit counter and a 2 to 4 decoder. So, what this 2 bit counter is a standard counter. So, it will go from 0 0 0 1 1 0 and 1 1. When 0 0 is given as input, so T0 is made high. When 0 1 is given as input, this decoder will make T1 equal to high. So, it will go like this. So, that way we can get a decode counter and we can realize it. Another counter is known as Johnson counter. So, this is also known as twisted ring counter because it requires less number of flip flops. So, it is counting in the sequence like say 0 0 0 to, it is counting in the sequence like 0 0 0 to 1 0 0 1 1 0 1 1 1. So, it generates all the 6 patterns, it goes in a mod 6 fashion. So, the advantage is that your number of states that you are getting is twice the number of flip flops. So, we have got 3 flip flops, but using 3 flip flops you can get 6 different patterns. Okay. So, that type of, so this is known as Johnson counter. It counts in this particular sequence 0, then 4, then 6, then 7, then 3, then 1, then 0. So, this is the corresponding circuit of the Johnson counter. So, you can just trace through this circuit and see that it really generates a count in that sequence. So, the state transition diagram is like this and you can get the corresponding circuitry from there. So, finally, in a 4 bit binary counter, so we can have the generic binary counter may have this load facility, count up facility, clear facility which will clear the counter. We can load the counter with some initial value, and so when this load input is given and this data input is coming. So, this that is loaded into this 4 bit counter and it goes like that. So, this way we can design a generic counter which has got the parallel load facility also. This is similar to this shift register loading, and with that the counting facility is added.